Solving a 4,000-year-old textbook problem. I call it a textbook problem because it appears to be just a learning aid for the students back in Babylon. The Babylonians used what we know as base 60, whereas today we use base 10. The way to think about it is that we have 10 unique numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. They all have a distinct, unique shape. After 9, you get 10, which is unique in its name. However, in its written form, it is just composed of two numbers we have already seen before, a 1 and a 0. The 1 meaning that we have moved up in magnitude. In base 60, there are 60 unique symbols. And these symbols in cuneiform were just little divots from triangular sticks pushed into wet clay. The purpose of using base 60 is its divisibility. Today we use base 10 and calculators. When we divide by 10, we get a decimal, but we don't have to deal with it so often because our calculators will do the work for us. In a time before calculators, or at least calculators that you could take around with you as you went shopping, the easier thing to do was have base 60. Because of the divisibility of 60, 60 can divide by 1, 2, 3, 4, 5, 6. This is the lowest possible value that includes the most possible amount of factors between 0 and 10. Say you went to the store and you wanted to buy something like rice, and they would weigh it out for you, but the price of the rice was measured in whole units. In this case, 10 or 0.60 units. If you wanted half of that, that would be 30. If you wanted a quarter of that, that would be 15. If you wanted a fifth of that, that would be a 12th. If you wanted a sixth of that, it would be a 10th. And you could easily weigh this out. This is the purpose of base 60, its divisibility. And this was the purpose of this textbook problem, to help kids know what reciprocals were, what two values multiplied together would get them a whole unit. In this case, a whole unit is 60. So implicitly in this question is something that we as English speakers might miss. The weird words, what I'm going to call the EGB and the EG. The EGB and the EG are actually reciprocal values. So the question reads, the EGB over the EG, 7 is beyond. The EGE and the EGB are what? The EGB and the EG are like a number and its reciprocal. If we had the number 8, its reciprocal would be 8 to the power of -1, or 1 over 8. We could write it like 8 over 1, and its reciprocal 1 over 8. And if we were to times 8 over 1 by 1 over 8, we would get 1, a whole unit. This is true of the EGB times the EG. We would get a whole unit. We would write it as 1, 0, or we can convert this over. This would be the same as 0, 60, because it is base 60. And just like that, it is the case that 8 over 1 times 1 over 8 equals 1. Well, 8 over 60 times 60 over 8 would equal 1. But if we convert that 60 into its whole unit and call it a 1, what would be the value we get underneath the fraction? What would be the EGB? What if we also don't know what the EG is? Well, we could write x over 60 times 1 over y equals a whole unit. However, this is the way in which we write it. If we try to convert 60 into 1 for the x part, we would then get x times 1 over y equals a whole unit. And in this way, we're starting to confuse ourselves. This is not how the Babylonians did it. We have to write it in a different fashion. We could write it as 1 minute, 0 seconds, or we could write it as 0 minutes, 60 seconds. It's the same thing. If we are going to convert 1, 0 to 0, 60, then we also need to do the same to the x value. And we will write 0, x. We can now see x times y will equal 60. We can now see the values on the right-hand side, the x, y, and 60, go together. We get x times y equals 60, or a whole unit. This textbook problem implicitly has the fact that they are dealing with reciprocal values, the EGB and the EG. But for our knowledge, it's important to remember that they're looking for this product, that x times y equals 60, that x times y equals a whole unit, just as our base 10 reciprocals will multiply together and get us a whole unit. Let's write one long line, and it's our x line, or our EGB. And we'd make a y line, which is shorter, the EG. If we were to lay x over y, or the EGB over the EG, we would see that 7 is beyond, meaning x minus y equals 7. So now we have a set of equations. X minus y equals 7, and x times y equals 60. Well, how did the Babylonians solve this problem? Here's what they did. If you lay out the EGB and the EG on top of each other, and you rotate the EG by 90 degrees, and then you fill in the rest of the lines, you would get a box whose area is a whole value, 60. X times y, area, equals 60. But you can make the EG a box of its own, and then you can see EG squared, or we will call y squared. This other box here will be the EG times what's remaining, which is x minus y, which we will call b. So we can see then that the area of 60 is actually made up of y squared plus by. So we can say then that y squared plus by equals 60. So we will just move the y squared plus by equals 60 into the corner and save that for later. So how did the Babylonians solve this? Same way we would, by completing the square. If you take what is remaining, the b, and you cut it in half, if you were to move that chunk that you cut off under the EG, or the y squared box, then you would have what is still an area of 60. What we want to find is the EG, which would be the length of the vertical line if we were to subtract half of what was remaining, b over 2, in our case 7 over 2. But in order to know that, we need to know the length of this side. And once we know the EG, we can find the EGB, as the EGB is the y plus what's remaining, so the y plus 7. So, in order to find the EG and the EGB, we would need to have a square. That is why this is called completing the square. So we draw a little square in this corner. The area of the new square is composed of the shorter sides of our remaining halves, b over 2 times b over 2. Therefore, the area of this smaller square is b squared over 4. So altogether then we have y squared plus 2 1/2 by's plus b squared over 4, which is equal to a whole plus our new square, b squared over 4. Simplifying, this gets us y squared plus by plus b squared over 4 equals 60 plus b squared over 4. We will call the length w. So this area is w squared equals 60 plus b squared over 4. Therefore, the square root of w squared will be w, and w equals the square root of 60 plus b squared over 4. Well, we know that b is actually 7. So if we were to replace all of the b's in this equation with the known dimension, the known remaining value of 7, then our equation looks like this. And we get that w equals the square root of 60 plus 7 squared over 4. 7 squared is 49. So the square root of 60 plus 49 over 4. If we cheat here, punch it into a calculator, 8.5. Or, in the Babylonian terms, 8.5, which is 8 and 30. So then the length of this square is 8 wholes and a half a whole, 30 over 60. If we clean this up so we can have some more room. So then we can say that the length, w, equals 8 wholes and a half, or 30 over 60. The remaining is 7, so its half is 3 and 30. So we see then that the EG is w minus the remaining half, 330, or y equals 830 minus 330. And the EGB equals 830 plus 330. So then the EGB is 8.5 plus 3.5, 12. The EG is 8.5 minus 3.5, which is 5. So then our long line, what we originally started with, the EGB, is 12. And the small line, the EG, is 5. And we can check our reciprocals. 12 divided by 60 is 1/5. And 5 divided by 60 is 1/12. And that is how you solve a 4,000-year-old textbook problem about the EGB and the EG.